Now let's talk about approximate integration, which corresponds to section 7.7 of our textbook. And this is one of less important sections as far as exam preparation is concerned. As a matter of fact, since I began teaching in higher education since 1994, I've taught Calculus 2 many times, and I have never written any problem on approximate integration on any exams, and I'm not about to start now, especially considering that these kind of approximation schemes are getting less and less important due to the advance of those computer algebra system, which was discussed in the previous section. There are some theoretical importance here and there, so I may end up writing some project problem regarding this one, but definitely not exam. This is very tedious. So I'd like to stick to some theoretical aspects here. Consequently, I have to start from how does Riemann sums or the definite integral concept grew up. So let's review that part. How did we define definite integral? Well, Riemann sum and Riemann integrability began from the concept of partition, and let's begin with partition concept. So here's a review of a partition. Given closed and bounded interval a to b, a partition is a finite sequence of real numbers x0, x1, x2, all the way up to xn in strictly increasing order, where x0 is same as starting point A and xn is same as ending point B. Consequently, these n plus 1 numbers divide the original interval a to b into n pieces. In this particular case, 4 pieces because n is 4, and each subinterval has interval length delta xi, where delta xi is xi minus 1, and we denote the largest of delta xi's and to delta x, and that is called the size of the partition. Consequently, delta x goes down to 0, then all delta xi's go down to 0. Now, for each partition, we can define a Riemann sum kind of like this. Delta xi is size of each subinterval, and for each subinterval, we multiply by a representative of the y-coordinate value selected arbitrarily between the minimum and maximum value in that subinterval. Kind of visualized like this. Here, I want to see this in the same viewing window, so let's stick to this. And this program is randomized, so if I run this one multiple times, you'll see the height of each rectangle changes, and that's because yi star is arbitrarily selected between the minimum and the maximum value, which are visualized as horizontal dotted lines and dotted line segments here and there. And yi star can be selected anywhere in between, and consequently delta xi, which is size of the subinterval, which is the width of the rectangle, and yi star, those are heights, and sum of those areas of those rectangles becomes the Riemann sum. One more comment. Those yi star can be re-expressed as f of xi star if your function is continuous, but if it is discontinuous, you can't. Here is a visualization for each yi star arbitrarily selected. We have this crossing point between this graph and then this yi star, so we can find the appropriate xi star, so that f of xi star equals yi star. That's possible for first interval, third and fourth interval, but we can't do that for second interval in general because of the discontinuity. The top of the red rectangle does not cross the graph because of discontinuity. Consequently, we cannot find appropriate xi star. Here, we are not really interested in Riemann sum and Riemann integrability. We are interested more on approximation, so let's stick to continuous functions. Consequently, yi star is same as just f of xi star as we see in this visualization, and this is for arbitrary Riemann sum. Arbitrary in that both the selection of partition and height of those rectangles yi star values are randomized. So xi's are randomized, also yi stars are randomized. Consequently, we have bad approximation. And this one is a kind of Riemann sums that our textbook author discusses. Xi's are fixed, and the partition is fixed. We have same interval size, but yi stars are randomized. So we have a little bit better approximation, but to a certain degree. Now, kind of approximation that we are particularly interested in begins kind of like this: midpoint approximation, where yi star is selected as f of xi star, where f of xi star is, as a matter of fact, the midpoint, xi minus 1 plus xi over 2. So, oops, let me expand this picture. And please note that the graph cuts through the top edge of each rectangle exactly at their midpoint. All these corresponds to midpoint, 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 and so on. This kind of thing is used as an approximation scheme, and let's discuss how to calculate those, and then let's discuss how good they are. And the midpoint approximation we just showed you, let me show you again the same picture, can be rewritten according to this formula, and this is rather tedious. Not really tedious, excuse me. That midpoint mi is xi minus 1 plus xi over 2, the midpoint, so that's something we already discussed, and some algebraic manipulation will yield that this will turn out to be something like that, and that part is tedious and not really important too. So, well, here it is, and let's just rely upon it as a formula. And for some strange reason that this midpoint approximation follows this error bound. So the error, absolute value of the error, because error can be either plus or minus, is less than or equal to this right hand side, and that's kind of strange here. Actually not really strange. I want to convince you how this thing is coming about. B minus a to the third power, so the bigger the interval, the less accurate the approximation. That's normal, because if the interval you're dealing with is large, then there's more room for error. 24n squared. 24 is rather mysterious, but n squared is really not, because the bigger the n, the smaller the error bound, consequently the better the approximation, and that fits our common sense. Now k value is kind of strange, but it is a upper bound of second derivatives. If the second derivative have maximum, and the k will be the maximum, but it may not have the maximum, so we have to use some kind of upper bound. And what does that mean? Well, if your graph is kind of like linear or close to a line, kind of like if you have a interval very close to the inflection points where the graph behave kind of like line, kind of around here, then the approximation will be really good. And in a region where graph is more wiggly, kind of like around here or kind of around there, then the approximation will not be very good, because a second derivative tends to be large there. Please recall that the second derivative is related to the concavity. So that's how this is related. And about the computation, never mind. Trapezoid approximation is another good way to approximate a definite integral. It kind of done like this. Instead of using rectangles, approximate them with this polygonal approximation, and then use area of the trapezoid. Each individual trapezoid can be calculated like this. If you look at it from sideways, this is top and then the bottom, and then the height. So what do we have here? Yi minus 1 plus yi is top plus bottom divided by 2 times the height. Or you can use it as left plus right over 2 multiplied by the thickness. In any case, this is the area formula for trapezoid. And if you look at this one, yi minus 1 plus yi over 2, that turns out to be the average value between these two y-coordinate value, the middle y-coordinate value. So if I replace this one, yi minus 1 plus yi over 2 as a yi star, which is average value, then that corresponds to these green rectangles here in this picture down here. These two pictures are actually talking about the same trapezoid approximation, because each trapezoid we see in the top picture corresponds to each trapezoid we see in the top picture shares the same area as green rectangle of those corresponding interval of the second picture. Indeed, if you fix on trapezoid, for example, the second trapezoid we have over here where my mouse is, and if you take average of y-coordinate value, y1 plus y2 over 2, so if you take average, that corresponds to the y-coordinate of this green rectangle, second green rectangle here. And of course, that applies to all the rectangles there. So what is the moral of the story? Even though we began with trapezoids, the Riemann sum turned out to be rectangles again. Consequently, we have a Riemann sum that is approximating the Riemann integral. Basically the same thing as before. And not surprisingly, the error bound is pretty much the same, except for a factor of 2. Instead of 24 down there, we have 12. So error bound for trapezoid approximation is a little bit bigger, which means as far as error bound is concerned, midpoint approximation is superior. But essentially, they are very similar because they are in the same order. Now, if you use parabolic approximation, this font is kind of broken up, excuse me. If you use parabolic approximation, that's a very different story. We can use several parabolic regions to approximate the signed area, kind of like these. Here, each individual red regions are given by approximating parabolae and then region behind those. And approximation is this time done by not linear but parabolic, so computation is more complicated, and we have the formula like this, and derivation is not difficult but it's tedious, so I'm not going to do that. If you look at the error bound, well, we have different error bound, and most conspicuous here is n to the 4th power in denominator, which means this parabolic approximation will turn out to be superior in most situations. Instead of n to the 2nd power, we have the 4th power, so error bound decreases more quickly as n gets larger and larger and larger. What kind of exceptional circumstance? K is related to the fourth derivative, not the second derivative this time. So if the fourth derivative is really large, then everything is smooth. But otherwise, parabolic approximation appears to be doing a good job. Well, example. If you have some time to burn, you can do some example. But to tell the truth, if you have time to study these approximate integrals, I'd much rather advise you to study how to type in mathematical commands and then do the computation with computer algebra system. This topic is obsolete. Okay, that's it.